So, my third paper was on medical transformer, gated axial attention for medical image segmentation. Uh, the medical transformer is already a thing with the transformer being a hot topic right now. They probably quickly made because they're trying to use a lot of deep learning to do medical processes. So I'm sure they quickly made a transformer to try to do those processes. And then but these guys are basically looking at the gated axial attention idea for medical image segmentation. And it was written by these folks in Johns Hopkins, and the work was done by these folks in Johns Hopkins and Rutgers University. We'll break down the paper as an intro. They go into their methods. They go straight into their experiments and results, and then conclusion. Introduction, again, they explain image segmentation and how they're going about it nowadays. The COBNETs being used, UNet, VNet, these are some of the baselines that they use to compare. This is like some of the results. They even have a med transformer for D. It's kind of like a qualitative way of looking at comparing some of the standards. Then they explain how transformers, like I said, transformers started getting into the picture like before they used deep learning and the VIT, the vision transformer, started getting into play. Then Axial Deep Lab started getting into this axial attention idea, and then they want to propose this gated axial attention idea. Oh, they also use this local global idea that they'll explain later. And then they get into their methods. So they explain the medical transformer, but they explain they want to use this logo method with a local and global branch. And then they have a diagram of it here. So the global branch will look at the whole image and process it. And then this is like the current vision transformer method. They use like a window method. They call it patches. And then process each patch. And they do say that is faster, but adding this global branch idea kind of helps keep context of everything that's going on. Then they go over self-attention. Then they go into this axial attention idea where you only go over because attention works great in NLP, right? And then transformers start getting into these images. They want to start using them on images, but images are like two-dimensional. I mean, I guess you can call NLP one-dimensional. So axial attention, yeah, it only looks at one dimension at a time, the length and the width. And then this gated axial attention that they want to use, it's kind of like, it has a it has this G learnable parameter in it. It's kind of like the efficient net, or efficient net isn't learnable, it's adjustable. Not like efficient net, but yeah, it has this learnable parameter. Oh, it's kind of like the growth decay idea for parameters in a deep neural net to adjust accordingly for the keys, queries, and values, and the attention across each dimension. Then they go into the local global training idea that they use the whole image, and then they break down for the patches, or I call it windows. 16 patches of they break down the image into 4x4s. They divide each dimension by 4, and then they get 16. They call it clock I, and then they get into the results. The data sets they use are the US brain data set, gland segmentation data set, and this MoNu-seg data set. They use cross entropy loss, a batch size of 4, the atom optimizer, learning rate of 0.001, 400 epochs. For the first 10 epochs, they don't activate these this gate idea. They just let it be, and they use NVIDIA 8000 GPU for their experiment. They compare it to UNet, UNet++, Res UNet. Then they use the F1 and IOU scores to quantify things, but they mostly focus on the F1 score. So here, the Brain US data set is the largest data set, so all of them are generally doing better, but still the gated axial attention does better than all of them. And then, yeah, like in the smaller data sets, gated axial attention kind of doesn't do so well, but they explain that there's like there could be more benefits to this, like on smaller data sets. Then they go to this ablation study. Then these are like more qualitative results of the attention, or the axial attention and the UNet. Like it's qualitative, but like the like you can see this square is kind of a little shifted. Like this one's kind of in more. You could barely see the difference. Like ResNet is like all the way on the right here, but it's actually right here. So like I think the quantitative results are better, but yeah, they have that right there in the middle of their ablation study. But then they get the ablation study table. Then so the first ablation study, I think they're looking at the logo results. Ablation study shows that each individual, oh no, yeah, the ablation study, that's like kind of the meaning of it. They go into each component kind of adds up to the final product being the best. Like there's UNet, then there's Res UNet, then there's Axial UNet. Axial UNet does better than Res UNet. Gated Axial UNet does better. Then Global does better than Local. And then you put Local and Global together and does better than both of them. And then Med Transformer at the end just does the best, which has different parameters of that inside of it. Then they look at the number of parameters. So they have this UNet and then this UNet mod. They took the number of parameters. Inherently, UNet has like 3 million parameters, but they just modified it to only have 1.3, because then it'll be a little bit more comparable to what their inherent parameter count is. And then they have ResNet mod. They did the same thing, and inherently has like 5. So But also, even between themselves, like, it still does relatively the same. Well, this one at least. But yeah, even with the more parameters, it still can't compare with the gated axial unit. And then bringing it back down, still doesn't help. It even improved the unit here. And then yeah, they explain their results and their conclusion, and that's it. Like I said, my email is savinN at 49 or 49 at students@rome.edu. We can like talk more about ideas in this paper. Over 5 minutes, but I tried to get it in 5 minutes this time. All right, maybe next time.